fact, now we did a lot of Coulomb's law problems. Don't forget that if you have more than one charge, you use superposition. And that would mean that the force, the net force, on any given charge is going to be the sum of all of the individual charges. So there'll be some F1 from some charge 1, and some F2 from some charge 2, and some F3, and so on and so forth. So you just add up all of the different charges. Now, I've got a few examples of problems like this. I'm going to use the big Mamma Jamma eraser. Sweet. Love it. I'm going to get one of those.
To use on an amazing board.
That board is amazing. I want that board. Oh man. Get that eraser with that board.
When's your birthday again?
October 11th. Yeah, it was my first quarter here. All right, so one example that's kind of nice. This is an example out of the book, but I like it. And there's other examples too. I'm not going to do all of them, but I'm going to show you this one at least. If you have some plus charge right here, I'm going to call it Q1, and some other plus charge over here, I'm going to call this Q2. Where is the force equal to 0 for a charge Q3? So I want to take some charge Q3 and I'm going to put it in there. Also, I think the distance between these, I'm going to call it D, and that's equal to 10 centimeters. So I want to put some charge, oh, and also something else is given. Q2 is equal to 3 times Q1. So Q2 is 3 times as strong. All right, so we can go ahead and test by trying to put Q3 in a bunch of different places, right? If we put Q3 over here, well, what's the direction of the force on Q3 from Q1 going to be? The direction, yeah, that way. Okay, so that's F1. What about the direction of the force from Q2? Yeah, it's going to be in that direction like that. That's F2. So clearly, that's not going to work for finding a 0 force over in this region right here, because they both add together in that direction. Same thing over here. Q2, the force from Q2 is going to be in that direction. The force from Q1 is going to be in that direction. So it's got to be somewhere in between here where the force from F1 is in that direction and F2, oh, it's going to be on the, going to be closer to this other guy. F1 is in this direction and F2 is in that direction, okay? So likewise, it can't be up here anywhere because now we're going to have some, although some of the components will cancel out, you're going to get a net force in that direction. So it has to be on axis, it has to be in between Q1 and Q2. So that's the setup for the problem, right? Just determining where this is possible. Then the next thing is figuring out how to do it. And I would start by defining the distance from here over to here as x, and then setting it up. So we know that, well, in this case, we want the magnitude F1 to equal F2. So let's go ahead and figure out what each one of those are. F1, that's going to be K times Q1 times Q3 divided by, let's see here, the distance between Q1 and our particle Q3 right here. That's going to be over x squared. F2, that's going to be K times Q2 times Q3 over, all right, this is this distance right here. That's going to be D minus x squared. All right, so you set these guys equal to each other. You get k q1 q3 over x squared equals k q2 q3 over d minus x quantity squared. And you start canceling stuff out. So this guy goes away, and that guy goes away. Q3 goes away. And so we also know something about Q1 and Q2. We know that Q2, that's going to become 3 times Q1. So the Q1s will cancel out. And we get 1 over x squared equals 3 over d minus x quantity squared. All right, now we just use our algebra skills. 3x squared equals d minus x squared. If you multiply this all out, what you end up with, and I'm not actually going to solve it, but you end up with 0 equals 2x squared plus 2dx minus d squared. You can go ahead and do that for yourself. And this is a quadratic. Use a quadratic formula. You can plug in all the numbers that are given, and you'll get 2 answers. You'll get x equals 3.66 centimeters, or x equals negative 13.66 centimeters. And these are both valid answers for when the forces are equal, but one of them is like way over here. We already decided we couldn't use this region, so this is our answer. X equals 3.66 centimeters. That's like right there, okay? Oh, I guess it's closer to that guy. Anyway, so that would be a good example of some problem that I would ask for from this section. Also, other examples would be like if I have some positive charge here, some negative charge here, some positive charge here. I'll give you some geometry that's easy enough to solve, like this is 4 centimeters, 3 centimeters. I think this may have been a quiz problem, or maybe it was a group work problem. And you got to find the force on this guy right here. So I'll call this A, B, and C. And I'm not actually going to do it. But what I will say is that the first thing you do before you start breaking anything up into components, before you do anything, is you just write the vectors down, which direction the force is going to be. Which direction is the force of C going to be from A? Down, right? So draw that vector, F, A, okay? It's going to look like that. And which direction is the force of C going to be from B? Point with your finger. Yeah, that direction right there, right? So before you get started doing any math, draw this, F, B, okay? And you can see that the net force is going to be something like that. Well, not exactly. Maybe like that, okay? But do that first so you can kind of check your answer, right? If you get some answer and x is positive, you probably have done something wrong. So before you get started, draw the diagram. Make sure you take into account the signs. Opposites attract, likes repel. It was very common on the quizzes to have people just assume that everything repels or assume that everything attracts and not think about the signs explicitly first. Yes?
For the last one, when you set them equal to each other, why didn't you make one of them negative since they're going in opposite directions?
Right here?
Yeah.
That's a good question. So, because I wanted the magnitudes of them to be equal.
Okay.
Okay? So,
You don't care.
I could have made one positive and one negative and used the proper vector notation and everything like that, and it would have given me the correct answer.
Okay.
But it's just another step that I didn't want to do.
Okay.
Okay. But yeah, I just knew that at this point the magnitudes of these are equal. Screw the vectors. I just set them equal to each other. Okay. So that would be another example. And then you just use superposition. So you're going to add up, well, you're going to calculate the magnitude of this, you're going to calculate the magnitude of that, and then you're going to break them up into components, just like you would in your free body diagrams, and add the forces together to get F net. Okay? And of course, you use Coulomb's law to calculate the magnitude of each of these forces. Yes?
F is equal to EQ, right?
F is equal to EQ. Yes. And we'll get there in a second. Oh, is there anything else from this chapter? Oh yeah, a couple of other things. Other problems would be if I had other forces involved. In that case, right, you're just going to draw your free body diagram, and you'll have, you know, some force of gravity pointing in one direction, and some force of the some electric force, okay? And then you would go ahead and do whatever dynamics problem I am asking you about, or maybe it's a static equilibrium problem. I think you had some like this in your homework. There's definitely some examples in the book, but you know, you have other forces besides F sub E instead of just electric forces, and it just becomes another force in the free body diagram. You treat it like you would any other force, as you did in 141. Questions? And the last thing in this chapter is we started introducing the field model, which we expanded a lot in the next chapter. But in terms of this chapter, we talked about the fact that in order to talk about long-range forces, we can no longer say, okay, this force is directly in contact, or these objects are directly in contact. How do they even feel this force? And we developed this idea that the electric forces, or electric charges, they interact via field, and a field is this distortion of space. So you have a charge in space, it distorts the space around it, and if you put another charge in that space, it feels, whoa, it feels that distortion, and it feels it as a force. So, and we said that if we want to check for an electric field, okay, if I said, all right, how do I tell if there's an electric field here? What do I do?
Put a test charge on it.
Put a test charge on it, right? I put a test charge in the field and I test the force on it. So that's F on Q divided by Q. That's how we define the electric field. You take some test charge Q, it's positive charge. Test charges are positive. I put it in the field and it feels a force. If it feels a force in that direction, I say, okay, the electric field is pointing in that direction. If I take it somewhere else and it's pointing in that direction and it's less strong, I say, okay, the electric field there is now in that direction and it's less strong. As simple as that. You just test it with a test charge. But more importantly, what you get out of this, and most often what you'll want to use, is you'll want to say, okay, well actually, the force of a charge in an electric field is equal to F is equal to Q times E. So more often than not, that's what you're going to want to use. That's the force of a charge in a field. Okay? And that's why fields are important to us, is because if we put something in them, it's easy to calculate the force. Okay. And for a point charge, we said that the electric field was equal to KQ over R squared in the R hat direction. I think that's about as far as we got in this chapter, but this brings up one important idea, and that is the idea of a vector field. So if you have some positive charge in space, and it has some electric field that looks like this, okay, electric field from a point charge. Well, we can represent that by drawing all the vectors, or at least a select number of vectors in space. So that would be something like this, right? You find some points, and at each point you can draw a vector, right? Remember, the electric field is a vector, and it represents the direction and the magnitude of the electric field at that point. So this is 4 points. If I pick some point further out, r is going to be bigger. It goes down as r squared. So this will be some smaller vector, like that, and so on. And this is a vector field. Okay, the reason why I mention this is because in a lot of the labs, when they were asking for electric field lines, you guys were drawing vector fields instead. And a vector field is literally just drawing the vector that represents the electric field at each point. Okay, this is an aside really quick because we're not there yet. This is not the same as electric field lines, which just extend out into space like this. Those are electric field lines, and they're not the same thing, okay? So this is a vector field, this is electric field lines, not the same. So just keep that straight in your head that they're just not the same thing. They represent the same thing. They represent the electric field's direction and strength, but they do it in different ways. And so keep that straight. All right. This is called a vector field diagram, I guess. I'll use this straight eraser. I'll have 2 lines. And that is the end of chapter 25. Questions on chapter 25? Okay. It seemed like you guys did good on the homework. The homework was pretty straightforward. The labs were pretty straightforward. So, but still there's good opportunity for conceptual questions that, could potentially be tough. Okay. Chapter 26. This was sort of when things started getting more difficult because we ended up having to do the math to calculate the electric field. Now, remember, there's really only 4 basic things that we could do. And the 4 basic field models, we've got a point charge. Okay? And a point charge, it's like the most important one, really, because we derive